All right, welcome back. We are Game 2005 in the fall 2022 semester at George Brown, and it's week 2 of our broadcast and recording. And again, this is our lecture for this week. Last week we talked about the course outline. We also talked about we did a bit of review on geometry and trigonometry. We talked about those things. And we mentioned that triangles are really super important. Without triangles, you can't really do any physics. You can't really put together any kind of three-dimensional objects. Triangles should be your friend at the end of the day, right? If they're not your friends, you need to learn how to make them your friends. The other thing that we have to mention today is please don't forget your vectors. Okay, so vectors are super important because we're going to be using vectors throughout the time that we're game devs. We use them for everything, and so vectors. And then the next thing is matrices. So if you need to brush up on matrices, please do so. Without vectors and matrices, you can't really do OpenGL or any 3D graphics. All right, so you need to know those things, especially when it comes to the lighting calculations that you'll be learning about in OpenGL. All right, so pick that up now. Don't wait to remember that until the time comes. Start, thinking about those things now. This week we're talking about motion in one direction. Okay, and when you think about motion in one direction, you're like, what? Why motion in one direction? Why do we have to go so simple? But actually, it's kind of our foundations, our building blocks for what we're going to be talking about as we build, the whole physics ecosystem that we're going to be working with this semester. So we're going to be talking about something called kinematics. And really, when I think about kinematics, I almost think about telekinesis, right? I don't know what it is. I guess maybe it's the word kinematics. Me, I'm thinking telekinesis. I don't know why. But it means motion, right? And when I think about motion with kinematics, this curtain is driving me crazy. It's like it represents change of an object, right? But we can think about motion in two different ways. Sometimes we think about things like distance, and we're going to be talking about something called displacement. So before I talk about distance and displacement, what is the difference between distance and displacement? Does anyone know the difference? Yes? Okay, so the answer was distance. Displacement is a direction from one place to another, is what you said, right? Okay, anyone else have another definition for displacement? Don't look it up. Yes?
Water.
Displacing water, okay, no problem. What else?
Displacement is measurement from x and y over vector.
Okay, displacement is measurement from x and y in vector. Anyone else? Yes, in the back. Yeah. Okay, that's closer. So it's kind of like that. So distance is, if I was going to measure a path that I'm following, like you said, I measure the path that I'm following. If I start at one point in the circle and I go around the circle, that's a distance. What's the displacement? 0, because I started and ended at the same spot. Displacement is the separation between where I started from and where I'm ending. And usually if we put it on the number line, right, if I go in a positive direction, I've got positive displacement, which means I'm going forward typically, or to the right, okay? If I have negative displacement, it means that I'm behind the number line, like behind where I started, or going backwards or to the left, all right? That's usually what it means. So there's a distinction between displacement and distance, which we'll talk about in a second. We're going to be talking about different types of motion. The ones we talk about the most in this course are translational and rotational kind of motions. Actually, we do that in graphics as well, right? When we think about, we translate an object, we have a transform component, whether it's, you're doing something with, if you're using Unity or if you're using a little engine, as an example, we have a transform component, and the transform component has rotation, some kind of position and scale. right? And we translate our objects, our game objects, in three-dimensional space or two-dimensional space. Okay? One thing that we're going to be using is the particle model to describe motion. So even if an object is a car, right, we're going to be, in our mind, we should picture it as a single point, a particle, right? It's an easier way to think about something as opposed to thinking about things like, what's the center of mass? What if the front of the car is heavier than the back of the car, or longer or something? Don't worry about those things. When we think about an object, and we describe things at the beginning anyway, everything is a particle, right? So when we think about everything as a particle, then our calculations become a little bit easier to think about, okay? They're not accurate. And remember, most of the times when we do games together, we make games, right? We're not thinking about a simulation. We're not. We're thinking about how fun it is. We're trying to make it good enough to do what it's going to do. So we start off with our mind, kind of modeling everything as a particle. It makes it easier for us to conceive of this thing and solve our problems. The other thing we got to think about is an object's position. Again, remember I mentioned the number line? We have to think about, when we think about objects in one direction or motion in one direction, think about motion in one axis, on the x-axis or the y-axis, but not across both axes, right? And when we think about that, we can think about the start position on the number line, right? That's what I'm thinking. And then as we move in one direction or the other direction, we reference an object's position, kind of with respect to the 0, 0 point of the number line. There's always some kind of origin, and we're going to be talking about with respect to the origin. Where is my object with respect to the origin? Why? Because then we can calculate our vectors, and we can calculate displacement. One thing that Joss loves, and he's going to be talking about this, is motion graphs. Okay, if he hasn't talked about it already. And really, when we look at a graph like this, right, it speaks to us. You have to be able to look at a graph and understand what's happening here, right? So here, there's two axes, right? We have our time on the bottom, and we have our displacement on the left, right? If you think about this, right? So, can someone tell me what's happening in this graph? I want you to read the graph, take a look at the what it's showing you here. Tell me what's happening, yes? Down? Is it really up and down? Think about displacement. Think about starting off at the origin, right? Where did we start? Away from the origin. With respect to the origin, we started 30 meters away from the origin. That's what our start point was, right? And then what did we do? In 10 seconds, so these are seconds, right? Over a period of 10 seconds, this is how you would describe this. I'm just trying to train you for the language, okay? Over a period of 10 seconds, we went from a displacement of 30 meters to a displacement of 60 meters, okay? If I went 30 meters, 60 minus 30, in 10 seconds, how fast did I go? What? 20 meters per 10 seconds, which is? Translated into meters per second. 2 meters per second. How fast is that in terms of kilometers per hour? That's what I want you guys to be able to do. All right. What's 2 meters per second in terms of kilometers per hour? How do I figure that out? We need to be able to translate units like this. I'm not putting you on the spot. Thank you for answering. The point is, if I have 2 meters per second and I have 60 seconds per minute, then I multiply 2 by 60. Right, so it's 120 meters per minute, and multiply that by 60, and that's what your speed is. That's pretty damn fast, right? 2 meters per second actually is quite quick, right? So that's how it works. So when we describe this graph, if we look at it, it's really describing us. It's kind of telling us a story, right? That's what it is. And a lot of people get bored when they look at graphs. They're like, "That's really boring, right? It's just a little curve, right?" Also, the other thing is, notice that one thing we didn't talk about was, although you see that there's a little triangle there, right? We have a curve, right? So actually, it wasn't a linear distance. What we talked about just now, 2 meters per second, was the average velocity. That's what we talked about. The average velocity between, time 0 and time 10, right? It's not the exact velocity because it's a curve, right? So that's what we're going to be looking at, position time graphs to some degree this semester as well. We talked last time about equations, right? And I got you guys to look at some equations using Desmos, which was a mapping tool that we used in real time. And when we're looking at Desmos, right? And I'm trying to map, from one axis to the other. We're going to be looking at tables like this a lot, right? So again, if I gave you a table like this, right, you should be able to create your curve. You should be able to create your position time graph from a table like this, right? Where we have one axis, so time in seconds, and another axis, right, in meters, the displacement in meters. I'm calling it displacement in meters because it's a position time graph, right? You can also visualize it as distance, though, depending on what we're looking at, right? One thing is what we're going to be doing is there's a lot of representations, is what this slide is telling us, and how to, kind of represent the motion of an object. In this case, the motion of that car we saw on the number line, right? So again, we can look at it from an image perspective, tabular, which is the table, mathematical, which is our equation, and so on. So different representations for doing the same thing, okay? And there's a lot of alternative representations as well. Okay, here we go, some equations. And I'm just going to zoom in here a little bit just to make it so that you can see this maybe a little bit clearer. Okay, we just talked about displacement. And okay, so funny marks that we're going to see, and for those people who've never done any kind of calculus or anything like that, it's okay. That big triangle is a delta, right? And forgive me, please, I'm not trying to dumb it down or anything else like that. I want to try and get everyone on the same level when it comes to our terminology, right? So, and there's no shame in anything like that. My expectation is that either you might have done some high school calculus or not, and so this way I'm going to talk about this. So when we see this triangle, in your mind, I want you to think delta. Okay, delta is the Greek letter. Delta means change, right? There's a small d for delta, and it kind of looks like a little funny d that's curved. And there's a delta that looks like a triangle, okay? So we say delta x is equal to, and whenever we see these marks, x and then lowercase f minus x and then lowercase I, or subscript I, what do those things mean? And please forgive me again, I'm going really super slow. I want you to be able to look at it and go, okay, I know what Tom wants, right? So what does xf minus xi mean? What does that mean? Yep. Hey. Final minus initial. So when we look at it, it's the position final minus the position initial is the change, overall change over the x-axis, right, which is our displacement. The units are in meters. That's typically what we say. And we can say that delta x can be both positive and negative depending on the direction you're moving, your vector, right? So if you're moving in a positive direction across one axis, here we're using x, but it could be the y-axis. It could be the z-axis. It doesn't really matter, right? If you're moving in a positive direction on the axis, we're saying we got positive numbers, right? If we're moving in a negative direction with respect to the origin, we can have a negative displacement, like we said before, okay? And we talked about this, that it's different than distance because distance is the length of the path followed by the particle, where displacement is the change with respect to the origin, okay? And we look at this, we can picture this as the differences here when we look at something like a basketball court, right? If we go, kind of from one side of the basketball court to the other, and we're looking at displacement, if I start here at the left and I go over where on the other side to the right, we can say the amount of displacement is the length of a basketball court. But if I come back, the amount of displacement is 0 because we haven't moved with respect to the origin, right? However, the distance is, you start at one side, it's like 2 lengths of the basketball court because we're going from one side to the other and then back. That's the total path that's covered, right? And maybe we're talking about these things because at the end of the day, if we look at the formula for displacement, right, and we say that the total displacement or change in x is x final minus x initial, if x final is equal to x initial, therefore it must be 0. That's really, that's how the equation works, okay? X initial being 0, x final being equal to x initial, right? That's what that means. We're going to also talk about some terminology. When we say vector, right, we know what it means. We talked about that last week. A vector has both, distance or direction and magnitude, right? Some kind of angle, right, away from the origin. We talked about angles last week as well. And then we have magnitude, which is the total length, if you will, of the vector with respect to the origin, okay? So that's one thing. Scalar, though, is a different thing. When I say, position, rotation, and scale means I want to either scale a vector up or I want to scale a vector down, almost like I'm magnifying something, or minifying something. With respect to velocity, so when I say velocity, I want you to think about displacement, okay? Velocity and speed are different things when it comes to physics, right? Speed is, kind of related to distance. Velocity is related to displacement. That's a totally different thing again, right? So you can see here that, with these deltas again, we're looking at these deltas. Delta x over delta y, the change in the displacement, right, over the change in time. If you think about this, we're starting to think about this in terms of the rate of change. The rate of change of displacement, I can kind of say, when I look at this delta x over delta t, because I'm changing time, and if I do something over time, I'm doing something with a particular rate. A good example, I want to do push-ups, okay? I want to get fit, like I want to do young guys, right, or young girls, right? I'm doing push-ups, and I want to do 20 push-ups every minute, okay? Like this guy over here, right? And, we can say that that's the rate of how many push-ups I can do. It's usually a rate, how many I can do per some length of time. How many per minute. I want to rotate, a motor, X number of rotations per minute. That's the rate of rotation per minute, right? I want to change my displacement over time. The rate of change is what I'm talking about. And once we talk rates of change, this is where calculus really helps us out. Calculus always talks about the rate of change, over time, right? That's the kind of way it works, right? Here we're not talking about that, but the equation we can take that initial equation, which is, position final minus position initial, and we can put it over delta time, and so we can, the equation on the right there is the same as the equation on the left for us. So if I say delta x over delta t, it's the same as saying x final minus x initial over delta t, because all we're doing is we're taking that delta x and substituting for x final minus x initial. That's all I'm doing. A lot of times when we do those kind of substitutions, you're going to see them. And physics solves these problems by either, kind of swapping out the components of the equation, the components of that one thing, whatever it is that we define. If I define displacement as x final minus x initial, anytime I have displacement, I can just plug in x final minus x initial, and we'll keep doing that over and over again. Okay, yes?
What is the equal sign of three lines?
Approximately equal to, right? Because it's an average, right? Yes?
So would T also have like a final and initial, like?
Yes, a t will also have a final initial. You're absolutely correct. So you can actually rewrite this equation as x final minus x initial over t final minus t initial, where t final is time in seconds, or how long it took for us to get from, to complete the motion, whatever that motion is. So very good, yeah. And so you can swap these out. And once we start thinking about swapping them out, we're thinking, okay, now I can create more complex equations. I'm building a foundation, building blocks of motion with these equations. Oh, one thing it says here at the bottom is also the slope of the line in the position time graph. The slope of the line, okay, which was what we saw earlier. If I go back to that little graph that we had here, this one, and if you look way up here at the triangle, that blue line is the slope of the graph, right? From, t final minus t initial, x final minus x initial gives us that slope of the line, right? Okay. Again, which is the average, right? It's not the exact amount. That's why it's approximately equal to, from an average perspective. Now, what about average speed? We talked about this just now. We said that speed doesn't have anything to do with displacement necessarily. It has to do with distance. So that's the path length. So again, if I'm doing pathfinding and if I'm going from point A to point B, sometimes point A to point B does one of these weird paths, right? It kind of winds or snakes along to find the shortest path, as an example. But you're going to see that if I snake to get to the path, it might be a long path, a much longer path, but the displacement might be much shorter than the distance, right? Because in your mind, I want you to think of this. The displacement is as the crow flies, point to point. I don't care about the path. I have no care about the path at all. All I care about is I start here and I end here. That's the displacement. Distance could be one of these, right? Even winding back on itself. You don't know, right? That's a totally different thing. So when we say speed, the average speed is distance over time. A lot of times, guys, it's simple for us to think about distance over time. Even though we're thinking about displacement, in our mind, especially as programmers, many times we just think distance over time, right? Because distance over time is speed. Again, we don't care about direction when it comes to distance. Distance doesn't tell us anything about direction because distance is not a vector. Distance is a scalar, right? Okay, so we talked about this. I'm just going to move on. Sometimes I want to know the instantaneous velocity. I want to look at the position time graph and I want to go, what's the instantaneous velocity at this point in time? And how do I find that kind of thing? And instantaneous velocity is almost like a time slice. If I was going to look at it from a computer perspective, for this particular frame, what is the velocity that I have of the particle on the engine? How fast is it actually moving? At this particular time slice, right? And this instantaneous velocity is happening at every point in time on the graph, okay? When I have instantaneous velocity, I can also infer instantaneous acceleration. And we'll talk about that there's a relationship between position, velocity, and acceleration. And what we can do is we can derive our position, our initial position, from our velocity. We can derive our acceleration from our velocity, and we can go back and forth. Those derivations, which I'm going to show you, is the basis for why we use calculus in physics, right? I can get the first derivative. If you've ever done calculus, if I can take the derivative of the position, I get velocity. If I take the derivative of velocity, I get acceleration, right? And we'll talk about the differences between those two things. If I want to go backwards, right, I want to get the integral from, that's what we say, the integral from acceleration, we go backwards to position. So if I have an acceleration, I'll give you acceleration, I can get the integral and get the velocity. From velocity, I can get the integral and go back to position. And so that's why calculus is so common when it comes to quick calculations of position time graphs. However, for us, there's no calculus, so we're going to go slow. A lot of times when we look at the instantaneous velocity, I want you to think about it as a tangent to the curve. So here's our curve, and I want to get this tangent to the curve at each point in time, right? So when we think about this tangent, right, like it says here, the blue line between positions A and B at different points in time, right, is the tangent, right? And that tangent is the instantaneous velocity at different points in time as I'm moving across the curve. Okay, that's what's happening, okay? The instantaneous velocity. So again, slopes are important as well because we can also, if we have a tangent I can take that, any kind of line I can take, and if I graph the line, remember, I can decouple the components, right? I have components, and on a 2D graph, I always have x and y components. And I can decouple those components. I can kind of calculate the x and the y by using, a lot of times, Pythagorean theorem, or some of the stuff we talked about last week, which is, hey, it's a triangle. I want to solve this triangle. How do I solve that triangle? Well, you know what? If there's a line and it's on a graph, I know there must be a right angle, chances are, right? Which means I can try and figure out the slope. The slope is the instantaneous velocity at that particular point in time, right? So we can get like a bead on how fast it was going at that point in time. Here's the instantaneous velocity equation. Again, going back to calculus, we can say that when we look to this lim thing, it's the limit. And we're not going to talk limits because, again, we're going to just scratch the surface here, so don't panic. I'm not going to bring this up on an equation on a test or something like that. But we can see that as the change in time approaches zero, right? Change in time approaches zero. We can kind of look at the delta x over the delta t, the change in displacement over the change in time, as dx over dt, and dx over dt, once we start thinking about that, we're thinking about calculus. We're thinking about derivatives. I can derive the time, as an example, and I get the instantaneous velocity from this little equation. Okay, so I'm showing you the equation. We're not going to do anything with it right now, but that's the velocity. Because the velocity on the x-axis, the instantaneous velocity, is as we're approaching that particular time, whatever that t is. If I'm going from t0 to t1, as I'm approaching 1, how many numbers are there between 0 and 1? Like I'm talking about in real numbers, infinite, right? So it's it's an infinite amount of numbers, right? So if I was going to start thinking about all those numbers, it's too difficult to calculate. I could time slice. I could kind of create little small little rectangles of time, right, to try and get closer and closer to that that time value. But it's easier for us just to think about it is the time value, right? So instead of thinking about just as we're approaching, when I say as I'm approaching a number, we can just think of it as the number. It's almost the same, right, in physics. Okay? So if I sub in values of x as I'm approaching a number, I can use those values to calculate the instantaneous velocity. That's what it means. Again, guys, I'm trying to ignore the elephant in the room, which is limits. Okay? Because for us as game programmers, it's not going to mean anything. Really, it won't. Okay. So we talked about instantaneous velocity, right? And when we think about instantaneous speed, it's only the magnitude of the velocity. So remember, velocity is a vector. All we care about for instantaneous speed is the magnitude of that velocity vector. Once we have that, we have the instantaneous speed as well. We don't care about direction because, remember, distance can go squirrely. It can go around and come back. We don't care about those things. Okay, we talked about velocity and speed, and we also talked about average. And we're going to be talking about average when we think about, if I think about averages, how do I do an average? If I'm thinking about descriptive statistics, who's done statistics ever? Anybody? Oh my God, some people have done statistics, some people have done it, right? And you're going like this, that means you kind of done it. So what are descriptive statistics? Anyone remember how that is? What are the three things we care about when I look at numbers in stats, starting off? Descriptive statistics. Okay, sorry, I know this is like grade 5 level math here, but it's mean, median, and mode, right? When we think about those things, right? The mean, what's the mean? The average, right? Okay, what's the median though? What's the median? That's where people get confused. Descriptive statistics. Which one? The middle number, right? So you have all the numbers. We have a distribution of numbers, right? And the middle number, the exact middle, is the median. It may not be the average, right? It may not be the average. What about the mode? What is that? The most common number, right? So if I have, like, let's say if we're averaging some numbers, if I'm playing D&D, okay? I'm playing D&D and I have 3d6 and I'm rolling, right? And if I roll 5, 5, 6, the mode is 5, because I rolled 2 5s. 5, 5, 6. My number, right, when I roll 5, 5, 6 is 16 when I add it together. My average is probably something like closer to 5, right? You know, that kind of stuff. And that's how it goes, right? So it's the same thing. So when we talk about averages in your mind, you're thinking about, if I'm going to give you an average time, that's why I take x final minus x initial, right? I kind of look at those that value, those values, and I divide it over time, over 2 a lot of times. If I have 2 values, I divide it over 2. That gives me the mean. If I have 5 values, I divide it over 5. Again, it gives me the mean. Okay? We're also going to use some analysis models when it comes to analyzing problems. What's going to happen is you're going to get a problem in physics, and it's going to say, you know, kind of like what we looked at last week, which was, you know, you have this distance from the building, and it's going to try and be confusing, right? It's trying to take a real-world example and translate it with some kind of equation, right? So we want to look at an equation, and really what is the equation? It's a model for us to help us understand the world, the universe, right? I want to understand the universe, so I'm going to put some kind of equation to it and go, okay, so here's what my perspective of the universe is with my equations, the things that I know. So that's what models do. They help us understand, you know, how to break down a problem. One thing I want to tell you is, and I want to repeat this from last week, is whenever you get a problem in physics, even if you give yourself a problem in physics, you want to do some kind of weird jumping or whatever, I want you to draw it. Like, first draw it. Draw the thing, draw the problem. Try and figure out and picture what, you know, what it is. Then start thinking about, how do I apply the equations that I know onto my drawing? How do I apply this? How can I translate this into something that's more realistic based on, you know, physics? That's what you want to do. So we're going to use an analysis model, and we're going to do a couple things here. It's going to help us, you know, with a particular entity. We talked about a physical entity, something that's in 2 or 3 dimensional space, and we also want the interaction between that entity and its environment. Okay, those are the 2 things we want. What is the interaction between you know, that particular entity? Again, we have different kinds of models we can use. We can use the particle model. We can use the system model. We can use the rigid object. We can use some kind of wave. Okay, just as an aside, light. Okay, physics, we're talking about light. Is light a particle or a wave? Someone said both. Is it? Do we really know? Right? It's almost like esoteric. Once I start talking about these things, I'm thinking about religion. Particles and waves together. I don't know. It's kind of really weird. Philosophy, right? You know, and it's kind of weird when I think about light. Okay, another really trick question just to get you guys going this morning, because you guys are looking like you're really bored right now. Okay, speed of light in a vacuum, what is it? You guys should be able to knock it. Come on, you guys should, you know, you guys are like game devs. Yeah? How much? No, the speed of light, not the equation of, not Einstein's equation, right? 300,000 kilometers per second. Okay, the distance between the Earth and the Sun in kilometers. Go. Huh? How much? No, it's 150 million kilometers, which is, what's that unit that we care about with when it comes with respect to Earth-Sun distance? Yes. 1 AU, 1 astronomical unit between the Earth and the Sun. Okay, so how long then? Let's do this equation. This is why I'm asking this. How long does it take for the sun's light to get to the Earth? 8 minutes, right? Isn't that funny? 8 minutes for the sun to get to the Earth, which means it takes 8 light minutes for it to go. It means if we were going to the speed of light, if I had a spaceship and I was going to go to the speed of light, you can't go to the speed of light because, you know, someone said E equals mc squared. E equals mc squared means that the faster I go, you know, the more energy I need, right? Which means as I approach the speed of light in a vacuum, that I would never get there because the amount of energy I would need would be infinite. That's why, by Einstein's laws, we can never approach the speed of light, which means we can never travel to the stars, right? By Einstein's laws, right? That's what we know so far. And isn't that interesting that it still would take 8 minutes for light to travel from the Earth to the Sun? Why am I talking about this? I want you guys to quickly calculate stuff in your head. I want you to do things that we talked about before. Meters per second, you know, and that kind of thing, right? Because it's going to come to the point where I want you guys to be, kind of comfortable calculating. Without the use of a calculator, by the way. All right. I know it's a tall order because it's the morning. It's 8 o'clock in the morning, and I'm trying to get you guys to think. Maybe some of you don't even have a coffee, right? So that's a bad thing. We have a motion graph at the top there, and it's marked this little red line. Let me bring it really closer here. I'll zoom in. On the video, you'll be able to see it, but you probably can't see it right now. Let's kind of zoom in right here into the thing there. So there we go. You can probably see that now. Okay. So you can see here that I've got this line, and question, what do you observe about the line? If you look at that red line, what is your observation about it? Observe, yeah. 5, okay, so there's 5 intervals. If we break this down, we can think about it in game terms as 5 frames, right? So I have 5 frames of motion, right, or 5 intervals. I like your intervals to think too. What else do you notice about the intervals? Do they look even? So 5, even intervals, right? They're exactly the same, right? Similar intervals. And it's describing a particle. It's motion, it's velocity, and it's constant velocity. That's what we want to think about. The velocity graph doesn't look like the vector arrows aren't getting longer. They're staying the same size, which means it's a constant velocity. And that's exactly what this is saying. So this constant velocity is the instantaneous velocity during a time interval, right? It's the same as the average velocity during that time interval. So we can say that then velocity, across the x-axis is equal to the average velocity, right? That's what we're saying here. It's kind of an interesting equation, and this is constant velocity. Let's kind of look at some of these other representations here. Oops. So we say that the mathematical representation of this situation is this equation where we have, the velocity on the x-axis is delta x over delta time, right? X final minus x initial, which we've seen before. Or if we rearrange the equation, you're going to see rearrangements like this a lot, right? How did they get to this? What did they do there to get us to do this? What was done, right? What did we do to get this? Algebra 101. What do we do to get this? How do I go from here to this? How do I do that? Yes? When I move stuff from one side of the equation to the other, what happens? If I take a term from one side and put it to the other, what happens? Sometimes we invert it, sometimes we multiply it by -1, depending on what the situation is. Right here, what we're doing is we're solving for x final. We're saying, if I want to find the final position, right? If I'm solving for the final position, I'm going to isolate this term, right? If I'm going to isolate this term, I need to move everything else on the other side of the equation. You see that? So here, on the left side, right, if we look at this entire equation, and we just block this out for a second, right, because this is equal to this. So let's just put our hand here for a second, right? And I have this, right, and I want to figure out this part, x final, right? Well, I start off by saying I need to multiply. I want to invert and multiply this one. So I'm going to take delta time. I'm going to put this on the other side of the equation. So I'm starting off with this side. I'm isolating the x. I'm taking this delta time, and I'm multiplying by the x, which is what you see here. Dx delta time, right? And then I have x final minus x initial. Minus x initial is minus, but when I bring minus x initial over to the other side, it becomes positive, right? So now I can see that I have x initial plus dx delta time. And that's how I'm isolating for x final, right? Algebra 101. You need to be able to look at an equation in this course and go, I see how to get it. All they did is move the terms around. If you're not comfortable with this, you're going to get more comfortable over time. It's just going to take time for you to get there, right? One of the things we do is we keep looking at something until we get it, right? Guys, you're going to get into a coding house, a studio, and you're going to take a look at code that's not your own, right? And you're going to be a little bit, you're going to feel a little bit weird about it. You're going to look at it and go, okay, I'm afraid. I have a huge code base I got to figure out. Don't worry about it. Because in a coding house, if you go to let's say some place like Ubisoft or whatever, they don't expect you to hit the ground running. It doesn't matter who you are. If you've never seen their Snowdrop engine before, they don't expect you to understand suddenly how to do stuff. They give you some time. And this is what you're getting here in this course. You get time to understand equations to some degree, and you get time to understand by it coming at you, you're seeing something over and over again, and it's going to be more natural for you the more you look at something. Okay. Here's something else that it says at the bottom. Common practice is to let Ti, T initial, becomes 0. And the equation becomes then x final is equal to xi plus vxt. Okay, let's think about what this means. Now we know what this equation is, and we're starting to come up with these kinematic equations, right? That means that I want to find the final distance. Let's translate this into what it really is, okay? I want to find the final distance. If I have an initial position, I want to find the final position. That's what I want, right? Let's translate xi into positions. Initial position, maybe somewhere in the origin, and I want to find the final position, and then if I substitute time, or delta time, Ti is 0, right? Then we can translate it to look something like this, where I can say the velocity across the x-axis, which is actually the average velocity, multiplied by time, which is easy, right? It means that I take my initial position, and we add the velocity over time. That's what we're adding, right? And then we have the final position. Okay, does that make sense? This is, again, for only constant velocities, right? If the velocity isn't constant, you can't use this equation. It's only for constant velocity, okay? Guys, stop me if you don't understand something, because it's like I told you earlier this semester, last week, I said, physics ramps. You start off and you're like, Tom's talking about triangles and geometry, and I'm really bored. God, I know everything, Tom, about triangles and geometry. And this week we're talking about, well, I can use calculus for this, right? And I'm skipping the calculus. I'm just showing you the code, the examples, this equation. Here, a question for you. How would you write this in code? How would you write x final is equal to x initial plus vx delta time? How would you write that? Because you're going to need to do this in code. You need to write your own kinematic equations here. So again, I would have a variable, final position equals to initial position plus the velocity and times time. That's what it is. I wouldn't even put delta in there, right? Sorry? Yeah. So we can look at a particle under constant velocity. There's a graph. This is what it would look like. It's not a curve. A curve, like we looked at earlier, was not constant velocity. It was a curve, right? And this is what constant velocity looks like because it's a number, a straight line, right? And we have a slope, and that slope is the instantaneous velocity at any point on that particular line. You can know it's the slope, right? Whatever that slope is, that's the instantaneous velocity at that point in time, okay? And it's going to be constant because it's not going to change. Constant means the same number all the time. Okay. So when we looked at a particle in constant velocity, now we're looking at a particle under constant speed. Okay, so this is something interesting, right? I have this velocity, and you can see I'm going in one direction, and then I'm going this direction, I'm going down that direction, and we don't care about this direction, but you can see if we make the same observation, that it looks to us that the direction, kind of the speed that we're having for each part of this particle is the same, right, over time, but the direction is different. And we don't care about direction because we're talking about distance, right? And if we were going to draw something, let's see if I can actually do this thing. If I was going to draw something, and let's go to insert, and let's go to shapes. And if I were to draw from this to this, like so, that is your displacement, right? So displacement goes from here to here. But you can clearly see in this graph that distance is longer. You've got more distance. If I was going to write that number down, the number for distance is bigger It looks almost by double, almost, if you think about it, than the displacement, if I was going to just estimate it. And by the way, humans are terrible at estimation, which we've talked about before. Okay? So then we can see that speed is distance over time. Just take that away. So here's something new. What about acceleration? So I have a car and I'm increasing my speed. We can't just say I'm increasing my velocity or whatever. We want to say how fast I'm increasing my velocity over time. It's the rate of change of velocity over time. Okay, hear what I said? Rate of change. Rate of change means, in your mind, motion graph, right? I have time at the bottom and I have a change in velocity on the other side, right? So velocity is my y-axis now, not position, right? Velocity is my y-axis. I've got time as my x-axis. The rate of change of velocity over time is acceleration. Okay? Once I start talking about rates, like I said before, in my mind I'm thinking calculus, rates, right? So here's the equation. So the average velocity, the average acceleration on the x-axis, or ax average, right, is equal to the change in velocity over the change in time. We can say similar things, like we said before. Let's zoom in on that equation, because you're going to need to know this as well. Here we go. Which is the velocity on the x-axis final minus the velocity on the x-axis initial over t final, right, minus t initial. There it is broken down, right? And that is your equation for the average velocity, average acceleration, right? What happens if I have a constant speed? What's my acceleration? Who said 0? You're correct. Average speed, you look bored, man. I'm so sorry. He's like something like, he's like this, he goes 0, like this, right? He's right, it's so easy, right? Because I said constant velocity. If I have a constant velocity in your mind, then acceleration's got to be, say it again, 0, right? 0. Because it's true. It's like, it's easy to think about this. If I have anything constant, then it's true, right? By the way, physicists don't like things like negative acceleration. They don't like to talk about that. Even like deceleration is a weird thing for them, right? They don't like talking about negative anything. They just say acceleration. The units might be negative at the end, but they don't say like, it's a negative acceleration. No, it's just acceleration, okay? Just letting you know. All right, so acceleration we talked about, and again, in one dimension, it can be positive or negative and can be used to indicate the direction as well. When we say instantaneous acceleration, again, we're looking at the tangent to the velocity curve this time. And I'm just going to bring this up again so you can see what this looks like. Okay, so some observations again. I want to get some more observations, and I know I'm going super slow, guys, but there's a reason for this, because you're going to make mistakes. When you look at something, you're going to be like, oh, I think it's this. Then you're going to think about it again. You're like, wait, no, it can't be, right? What? I'm going to go back to you again. Let's go for my, yeah, of course. Let's talk about I can come up to you, see, because I have a mic. So this is like a game show. Okay, go. So tell me about what you see. What are your observations? Frames. Okay, saying frames again. All right. What do you observe about the frames? What about the red lines and the blue lines? What do they represent? What's A? Acceleration is constant. So we're under a constant acceleration. If I have a particle, this is what we're going to say. This is our vocabulary. I have a particle under constant acceleration. Then what happens to our red line? What's the red line? No problem. What is it though? What's the red line? Velocity. You can see the velocity vector continues to stretch further and further. The magnitude of the velocity vector is moving bigger and bigger because the particle is under constant acceleration. So think about that. That means I'm putting on the gas, right? I'm kind of continuing to move faster and faster. That's what this means, right? When we look at this picture, that's what this is doing. It's moving faster and faster. The time between steps on the clock, as we think about this, which is frames, right? For the particles moving farther and farther away every frame. That's what's happening, and at a faster and faster rate of change of velocity. The velocity is changing over time, right? Thank you for that. So why am I talking about this? Because we need to be able to describe stuff in physics, and we need to understand what's happening, right? Rate of change of velocity over time is acceleration. Okay, and again, we can also estimate the acceleration in the instantaneous acceleration as the slope of the velocity curve. So now we have the first one, we had motion curve. We have a distance, kind of graph, right? We have distance on one side, or displacement, and we have time. Now we have velocity and we have time. Time is the same. And once we start thinking about time being the same axis, which is the x-axis, can we not then, kind of overlay both on top of each other? So I can have velocity and I can have position over the same graph, right? Two different colors, right? Talking about two different stories, right? If you think about them. And this is what this is. This is the instantaneous acceleration. And here it is. Here's this interesting overlay. That's what I'm talking about. So the top of the graph is telling us one thing, and there's another thing that's telling us over here, and a third thing that's telling us over here. The first part is the displacement time graph, right? Which is, if you think about this at the top, I'm just going to zoom into the graph just to show you this. So this is a motion graph, and it's telling us a story, right? The story that the motion graph is telling us is it's saying, hey, look, at the same time values, can we describe what's happening here? Is someone going to volunteer to describe what's going on here? Right, let's look at this graph. Okay, so I want you to tell me the story that this graph is telling you. Can anyone talk? Oh, you look really excited. Let's go. Tell me what it says. No? You don't want to do it? No? Oh, you look, how about my bored friend over here? Let's go, right? Tell me the story. What is this graph telling you, right? This graph, what is this graph telling you? This whole thing. What is the story of this graph? Talk to me about position, talk to me about velocity, talk to me about acceleration. What is this graph telling you, right? Going at a constant acceleration, okay. From where? From where? Talk to me about times, right? Because we're telling a story. Talk to me about the story. Right, and then? Okay, that's the acceleration. Now talk to me about the velocity. Talk to me about the velocity. What's happening with the velocity? Okay, so it's constant here, and then? Decreasing velocity. Yeah. 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 Good. We don't have to go further. You see what I'm saying? So what our friend here did is he correctly looked at it and goes, okay, I understand this is meaning acceleration. So what he said was acceleration is constant from 0 to TA, right? It's constant acceleration, then there's no acceleration, right? And then there's, again, we have constant, it drops back, right? And then what it does is it reflects on what happens with the velocity curve. The velocity curve, it looks like we have increasing velocity, right? That's the slope. Then we have constant velocity, then we have decreasing velocity. Remember, velocity represents displacement from the origin, and that's why we see that the effect on the position time graph. The position time graph is basically saying things, okay, so this is the time, this is the distance, or the displacement, right? So we're displacing away, and then we're coming back. Over here, we're actually coming back in this part of the graph, right? Because it's curving back down, right? Curving back down means the distance away from the origin is closer, which means we're going backwards, which is exactly the picture we're getting here, right? So we have a relationship. This is why I'm showing you this. There's a relationship between position, velocity, and acceleration. And you can read it on a motion graph like this. Guys, motion graphs are a great little tool. If I can build a motion graph in SDL, where we can play around with those curves, right? Then I can describe motion for a particle in time, right? Over time, which is kind of really cool. Joss is a fiend when it comes. Joss is watching this at some point in the future. Joss is a fiend. I'm saying this just for him now. When it comes to motion graphs, he loves them, right? And he's going to be talking about this with you, I'm sure, at length, right? And the reason why they're great is, again, they tell a story, right? And that's what I want you to think about. You know, physics can be really stupidly boring. You look at it and go, oh man, I'm looking at math all day long. My professor got me up at 8 o'clock. I didn't even have my coffee, and he's getting me to describe stuff. Or you can look at it and go, okay, so what does he mean here? Try and analyze what you see. Try to observe what's happening here, and then try and translate this into velocity, acceleration, and position, right? Again, guys, these are the building blocks. If you take this part seriously and you use this as a foundation, you'll understand how everything else works this semester as well. Okay. So that's kind of a description of that. So one thing to note, this is just an observation, is when an object's velocity and acceleration are in the same direction, right, we say that the object is speeding up. When they're in the opposite directions, we say that the object is slowing down, because we can have a velocity vector, you know, as an example, or an acceleration vector in a different direction than the velocity vector, right? Because my acceleration vector can be in the other direction, right? So I want you to think about that there is a relationship between force and acceleration. There's a relationship, okay? And you see that little weird symbol up here? Fx, and then there's a weird symbol, and then there's an AX, or alpha x, really what it is. Alpha represents acceleration, and then we have this Fx, which represents force. Sorry, this thing is like sliding down. Oh, there it is. This little thing here. Let's put it up here. There we go. So what does this little symbol mean in the middle? Okay, not the same guy. I can't have the same guy answer all the time. Someone else, yes? Sorry?
It looks like an unfinished infinity sign.
An unfinished infinity sign. Okay. It might look like that, but okay, thank you. That's good observations. What does it mean, though? Okay, does anyone know? It's proportional. That's what it means. When you see that funny little weird symbol that looks kind of like a fish, or an unfinished infinity sign, it means proportional. It means that the amount of force that's required to move an object is proportional to its acceleration. Let's say that again. The amount of force, that means, and if we equate force to energy, going back to E is equal to mc squared, where we convert matter to energy, and that kind of stuff. If I look at Einsteinian laws, right? If I need to increase my acceleration, I need to increase my force. And if I'm increasing my acceleration as I'm approaching, as an example, the speed of light, this is something that happens too. This is a weird thing for Einstein's laws, right? If you actually read anything about Einstein, if you're interested. He claims that our mass also increases. Okay, that's weird, right? Our mass increases to infinity is what he says, right? As we approach the speed of light in a vacuum, right? Which means we become fatter. I don't know how I can become fatter. I'm sorry, I'm not already fat enough, right? But I'm saying I don't understand. It's like you become fatter and fatter, right? It's actually not fatter and fatter. It's more dense, is what it means, right? You become denser and denser. Your particles, somehow you accumulate matter, right? That's the only way your mass can increase to infinity, right? If my mass increases to infinity, I need an infinite amount of energy. Going back to that whole thing, because I'm trying to push a bigger mass faster and faster. I need more and more energy. So my energy demands goes through the roof. And that's why we can never even approach the speed of light. Maybe we can get to, 10%, if we're lucky at some point in our human evolution for sublight speeds. And this is why we need something like warp technology, or something like that. By the way, NASA recently, over the last little while, I don't know if you've seen the articles, but they've been saying that they think warp technology is possible. They can figure it out, right, with some kind of warp field, right? So Star Trek was right, or so they say anyway. Hyperspace is another thing. If you believe in, if we're just talking science fiction, and as I digress again, hyperspace is another thing, because how do you go into hyperspace? You'd have to go into some other dimension where the time between ticks on the clock is different somehow, like time displacement, or maybe the distance is compressed, right? So meters become centimeters or whatever, so you can travel the same speed in hyperspace. You're not breaking any Einsteinian laws, but you're actually going further over time, right? Hyperspace. So this is the thing they're talking about. But this is an interesting thing, because we need to know this in the second part of our course, because one of the Einstein's laws, which we talked about last week, so the second law of motion, which is force equals to mass times acceleration. F is equal to ma. And if we know that force and acceleration are proportional, proportional means that the same amount, or approximately the same ratio of force to acceleration, then we know that mass is our limiting factor, right? I want to add force. If I didn't have mass, if I was a neutrino, right, if I have zero mass, then I could move as fast as I want, right, by just applying some force. But unfortunately, we have mass in the equation as well, okay? And because we have mass, it would take more force. Okay. We talked about this. Let's go this way. Again, I talked about this. Physicists don't like negative acceleration, because negative acceleration can mean negative things, so let's not talk negative acceleration. All right, motion diagrams. Let's continue to talk motion diagrams, right? Because I want to talk about these little things here. And I'm going slow, guys, today, and I do apologize. I'm doing this on purpose, because a lot of times students in the past, in previous semesters, have said, it's too fast, and I don't understand, right? It's true. I would go through 78 slides in about, 30 minutes or 40 minutes, right? And I would talk, and then record everything and say, watch the recording. And then, of course, no one watched the recording, because you don't do that kind of stuff. We don't read books either. So let's look at these four or three different, kind of pictures here. And, one thing we can see here, without asking too many questions of you guys, is when we look at the motion of the particle, we can see that in the top diagram, right? We can see that the car is moving at a constant velocity. We can see those time slices again, like you said, right? Time slices. We see frames, right? And we see in the second, in B, we see that we have an acceleration vector as well. And we can see that the velocity vector is getting longer and longer. So we're seeing that the acceleration vector and the velocity vector are going in the same directions, and that the car is moving faster and faster. You can see that the time step, every time step, the car is getting farther and farther away in proportion to the time, right? On the bottom one, though, we can see that the acceleration vector is in the opposite direction of the velocity vector, this one, right? The velocity vector is pointing to this direction, and the acceleration vector is pointing in the opposite direction, which means that now the car is slowing down. You can see how it is, how the car here is bunched up at the beginning, and the car is bunched up at the end, right? Bunching up at the end is like slowing down, trying to slow down, right? So this is kind of an interesting thing. And again, I don't think it's, mysterious what's happening here. You can see it. You look at it and you're like, okay, this makes sense to me, right? Because I can see it slowing down, whatever. It's just that we need to understand what the vectors are doing. That's why the vectors are here. That's why we're talking about acceleration and velocity. They're going in different directions. And this means that if I'm translating this into code, again, going back to code, then what I would do is subtract acceleration, right? If I'm calculating, let's say as an example, kind of the new position over time, right? If here I'm going to add acceleration, right? Because acceleration is moving in the same direction. Here I'm going to subtract acceleration. I'm going to use acceleration to modify my velocity, if you will, okay? In the negative. And that's what this is saying. So one thing also that I want to talk about again is that everything here is constant. Okay, there is no acceleration that is wildly different, okay? In this semester, and for our type of physics, everything for us is constant. A constant rate of speed, a constant velocity, a constant acceleration. Because otherwise, we can't use our funky kinematic equations, and it becomes more complex to calculate. Can you calculate speeds that are not constant? So what would be a non-constant acceleration? Within a time frame, I speed up and slow down at the same time, right? It's more difficult to calculate. We can use average acceleration for that, right? But typically what we think about is constant acceleration, all right? Because it's easier for us to model, okay? And that's what this is talking about here. This slide is constant velocity. This slide is acceleration and velocity going in the same direction. And this slide is acceleration and velocity where acceleration is going in the opposite direction. Okay? Okay. I'm just going to go to the next one. So when I think about kinematic equations, right? I'm going to think about kinematic equations here as an example. We can use these equations and exactly what it says here for uniform acceleration. Uniform means the same, okay? It means that I'm not going to speed up and slow down at the same time interval, right? And we can use these equations that we're going to talk about now to solve, most problems in one-dimensional motion. One-dimensional motion, again, means on one axis, x, y, or z, okay? We can apply the same things in any one axis. Okay, a lot of times we might need to use two equations because we can use two equations to kind of have the same terms, and each equation might tell us different information that we can use. One equation might tell us information we can use in the other equation. Okay, that's how typically what we can do. Two equations and two unknowns. Okay, or we can also think of them sometimes as a system of linear equations. Back to math. Okay, or algebra. So here's our first kinematic equation. For constant acceleration, or uniform acceleration, a across the x-axis, right? We can say that the velocity final across the x-axis is equal to the velocity initial plus acceleration times time. Okay, remember I said add acceleration if you're going in the same direction, subtract acceleration if you're going in the opposite direction. That's what I meant, multiply by time, right? So that is your first kinematic equation, okay? And if we think about this, and it doesn't give any information about displacement as an example, right? So that's what we can do here. We can start thinking about how we can use this equation to, to plug in some values. So here, if the velocity final is 0, right? If this is the information we're given, this first part, and if we use 9.8 meters per second, what's 9.8 meters per second? Again, we talked about this last time, huh? Gravity, right? And usually gravity is negative if we're looking at the y-axis, right? It's going in the negative direction, it's going down, right? So if I start off, and if I say that, the final position is on the ground, right? If the final position is on the ground, and the initial position is somewhere above the ground, 20, right? So I start with some ball or something above the ground, and then I use the acceleration of gravity over time. I'm dropping a ball from 20 meters in height, I don't know, it's way up there, right? I can figure out how long it takes to get that ball to fall from 20 meters down to the ground. 2.041 seconds. G is time. Let's go back, right? So let's go here, right? So what I'm doing is I'm solving for time.
Yeah, but what is not
Velocity, sorry, the same. It's actually the same thing, by the way. It doesn't matter. Yes, it's velocity. But we're talking about how long does it take? How does it, when I go from 20 meters per second to 0 meters per second, and I'm using an acceleration of negative 9.8. Actually, it could also mean, which we're going to see in the other equation. I made a interchange of equations. You're absolutely correct. This could be distance as well, right? You can use the same thing for distance, because when you think about it, right? If I'm solving for time, which is what I'm solving for, how do I do that? I take 20, put it on the other side, it becomes a negative 20. Right? Anytime we take a term and put it on the other side of the equation, right? And then I'm solving for time. I divide by negative 9.8, both sides of the equation, right? If I divide this side by negative 9.8, I got to do whatever I do on the right side, I got to do on the left side when I multiply. I'm scaling. If I scale the equation, I can scale both sides, and it becomes the same, right? So that's something interesting. Whenever we divide, if I want to get rid of something like this, and I say I want to divide both sides by the same, I'm not really doing that. All I'm doing is scaling both sides of the equation, right? So if I increase one side, I got to increase the other side, and nothing has changed, right? If I multiply both sides by 10, I'm scaling both sides by 10, who cares, right? If I'm dividing everything by negative 9.8, who cares? But if I divide everything by negative 9.8, then I can cross out negative 9.8 on this side, and I have, you know, negative 20 over 9.8 on this side. Right? Does that make sense? You have a question? So then that's why I get to this time. Yes?
Wasn't it like 9.8 squared, so it would actually be...
No. Divide. Not multiply. So if I have negative 9.8 here, right, and I want to get rid of this, I want to solve for t, right? And at first I pass the 20 over to the other side, it becomes negative, right? Then I have this negative 9.8. I want to divide both sides by negative 9.8. Because this thing is already negative, negative over negative is that? Positive, right? Therefore, the negative sign goes away, and I have positive sign. Yes?
What I meant was, well, I guess it's not actually gravity.
It's not, it is not.
Because
Negative 9.8 squared, yeah. No, it's not gravity. I'm saying, my mind, I saw 9.8, and I'm like, it's gravity, and then my friend corrected me. He says, no, it's velocity. He was right. Okay? So, but the point is that, one thing to note is this. Anytime we get negative time values, we should ignore them. If I ever get an equation, sometimes we're going to use an equation that's going to give us both positive and negative time values. It's almost like we make a curve on a graph, and it intercepts with the x-axis in two different positions. To the left of the origin, which is negative, and to the right of the origin, which is positive. We don't care about the left of the origin because we're not time travelers. There's no negative time, right? So we don't care about those values. All we care about is positive time values, like this one, okay? So again, it's kind of a weird thing. We're going to get back to this in a second, but you can clearly see if we plug in values, kind of our velocity, that we're, how we can manipulate the equation to get those, if we solve for time. So this could be a question like this. How much time does it take, for an object, right, to, that starts moving at a velocity of 20 meters per second, right? How much time does it take to get to zero if we have an acceleration of negative 9.8 meters per second? How much time does it take? That might be the question here. If I was going to reverse engineer the question for you, that's what I might ask you, on a test. How much time would it take, right, to do that, right? And then you sit there and go, okay, so he's asking for time. That means I got to plug in, I got to solve for time for this equation. What do I have? I always look at the stuff that I have that the question was given me. He's giving me 20 meters per second. That's the start. And he says that at the end, it's going to come to a stop. So 0 meters per second, right? And it tells me I've also got the acceleration, which is negative 9.8 meters per second, right? How much time does it take? Okay, here's the second equation. If I want to find the average velocity over the x-axis, we can say that, just like we said before, averages is we have two numbers and we divide them by 2. If we have three numbers, we divide them by 3. If we have four numbers, we divide them by 4, and so on, right? Here we have two numbers. We have x final, right? Velocity on the x-axis final plus velocity on the x-axis initial divided by 2. That's the axis, the average velocity. Okay? So pretty simple. Okay? We're going to do some problems in a second. Here's the third equation. Okay, a little bit more complex, but not much. X final, for a constant acceleration, x final is equal to x initial plus the average velocity across the x-axis, which multiplied by time, right? Which can be translated into, right? We can use both of these two equation parts, the left side and the right side, because it all is the same. All the right side has done is massage or sub in velocity x average, right? velocity x average, right? We've taken this whole value for the term velocity x average. We take this whole part right here, this part, right? We take that part and we sub it in. We plug it into velocity x average. We take that and we plug that in. And once we plug it in, we can separate the 1/2 because if we multiply anything by 1/2, we can kind of express it this way, right? We can say it's 1/2 times vxi plus vfx, and we can multiply it by t because that's what's happening here. You see that? Does anyone not see that? Okay, let's take a look at this again. Look, here. So here is this part here. If we're going to draw it, let's go insert again. This part here, if I was going to draw this part, which is not exactly what I wanted, but let's just make it so that it is just not no fill. So this part right here, right, Vx average, right, is just this part, right? So Vxi plus Vxf over 2. If we take that part and plug it into Vx average, and then we're left with this part over here, this equation, because this part right here, right, is all of this, right? And so what's happening is it multiplies by time. So, and like I said to you before, what physics does in math, we manipulate equations for our best, to our best advantage, if you will, right? So why? Because if I want to calculate, if I'm calculating, xf, which is our position final, right? And I've been given something like values of xi, and so let's say, for example, the initial position, and I'm given the initial velocity and the final velocity as an example. I'm trying to calculate the final position, and I also have time. I have everything. I just plug everything in. I'm good to go, right? And I don't have to figure out what the average velocity is because I've broken it down over here on the right side. Conversely, if I want to figure out time, right, and I have the final position and I have the initial position, I can just solve for t. Now, there's a little bit more challenge in doing that. So how would I do this? How would I solve for t with the second half of the equation? How do I manipulate the equation? How do I do that? How can I rewrite that equation in a better way for us? I want to solve for t, yes?
But that equation is solved.
This one. Let's suppose I want to. Let's suppose I have everything, but I don't have time, and I want to solve for time. I want to say, how long does it take with an average velocity of, I have an average velocity. If I have an average velocity of, 5 meters per second, and my x initial is, 0, and my x final is 10, as an example, what's t? Right? That's what I'm asking, right? Then again, I would manipulate it so that I would have t on the one side, and average velocity and the initial position and final position on the other side, right, of the equation. I want to move everything over, right? And when we move things over, let's do it together so as an exercise, right? So we can see how this works. So if I was going to rewrite this equation, right, then I might write something like this. T, right, is equal to, and let's just write lowercase t, right? T is equal to, and then if you think about what this looks like, I might do something like, I want to move over some values, so it might be something like this at the beginning. So t, and then, I don't know, times Vx average, right? Right, t times Vx average, because that's combined, right? That's equal to, xf, right, minus xi, right? Would it not? That's maybe my first step. Okay, because all I've done is I moved, xi on the other side of the equation. And when I move it to the other side of the equation, when I move it from this side to this side, it becomes negative. I multiply it by -1, right? And now I want to solve the next part. I'm sorry that it doesn't look the same, but let's do the next part. If I was going to solve for t, then I might do something like this. I might say, well, then t, I want to divide both sides by velocity average, is equal to xf minus xi, right? And we can say all divided by Vx average, right? And then we can take this further and we can sub in Vxi plus Vfx, right, as an example for this one. So it can look like T is equal to xf minus xi, right, divided by, in brackets, Vxi minus plus Vfx. Would it not? Do you see that?
Divided by
Hmm?
2, divided by 2, the last part.
Yes, divided by 2 is definitely something. Well, actually, divided by 2, that's something we missed. So that was here. This is divided by 2. Here, up here, right? We missed that part because we didn't do that. So this divided by 2 would be part of when we, sorry, let me go back. It's actually here. When we convert this from VFX average to this, so this would be divided by 2. Can we do this divided by this, divided by this? What does it become? If I divide something, and divide something, I'm actually dividing it by 2 over 1, which means I'm multiplying the top by 2. Which means it's actually 2, like this, right? Whenever we do something like that, if I divide something by dividing something, if I take xf over xi divided by vxi plus vfx, divide that by 2, I'm actually multiplying it by 2, right, at the top. So that's how it works. So that's how the equation would be, 2xf minus xi over vxi plus vfx. Thank you for the 2. I almost forgot that. All right, make sense? If it doesn't make sense to you, and if you're lost because of the stuff, please don't be freaking out. You're going to see more of this. We need to be able to manipulate algebra in this course. We need to do that algebraic manipulation. We need to move terms around, yeah.
The initial plus the final is divided by 2 is the average, or is that?
Yeah, so this is the average up here, right? Remember? Velocity initial plus the velocity final over 2, right? Because we're taking those two values over 2. Yeah, I know. That's what it is, right? So, and because we're doing this and we're dividing this term by this, then it becomes 2 times, right? And it's kind of hard to see because of my notation. I so apologize. By the way, if you ever want to, if I'm ever asking you to do something on an assignment, and I want you guys to use Word or PowerPoint to write it out, you can also use the equation part, all right? Which means I can, if I go to insert, let's pin this time, I can use equations up here. That's part of PowerPoint, and it's also part of Word. So let's rewrite this thing with equations. So if I say equation, right, I can type the equation in there. I can say T, you can see that works out nicely. And then I can start writing. And the great thing about equation is it gives us a script that we can use. So for example, I want to use, T, which is equal to Vxi. Well, there is this script area right here, just for you to write it. And what you can do is you can decide which one works best. We want to use a subscript, so I can use this one, right? And then now I have 2 spots. So this is, V, right? And this is on the bottom, we can click onto it, and that's xi, right? So that's how you can write it so it looks nice. And then you can, kind of multiply that by, or add, or do whatever you want to do. So you can say something like, well, I want to add in, and again, I can go back to this, and you can write it just like this, where I want to do the same thing. I can kind of write those equations so they look really nice here in PowerPoint or in Word, right? And by the way, if you ever do that, you just have to space over. You can make it look really, really nice like this. I'm just translating what this looks like right here. And this divided by 2. Remember that because this is an equation, you can also do this first. So you can say, well, this is all divided by 2, right? So you can say, I want to divide this. I can put that in place, or I can use this piece, this whole piece like this. I can kind of cut it out, and I can say that, when I insert my equation, I can start off with a fraction. And I can say that this part is the top part of the fraction, and that part is the bottom part of the fraction. You can have quite a nice looking equation, which is kind of what this is right here, right? Okay. You could also retranslate this. Let's just do one more time. You could say that this is t, right? You can also say that this is t over 2, right? So t over 2 times VFX over whatever, right? You can also say that because that is also something that is okay, right? Like, for example, something that looks like this. That is the same as this, right? All I'm doing is massaging it and moving it around. That's all I'm doing, right? And so this idea of manipulating algebraic equations helps us solve problems, okay? Okay, we're going to do more of this again coming forward. And I know I'm spending time on doing this because this is where people had issues and they came to us and said things like, I don't get it. How do I move things around using algebra? And they went online and they used some tool, you know, because there's tools online that'll do it for you, right? We know these tools exist. And then, of course, you'll do it. And then if I ask you a question, you can't answer the question. You don't, I don't know. I just plugged it into a tool and it gave me the answer, right? And then you wrote it nicely in on your assignment, but you still didn't understand anything. Equation number 4. For constant acceleration, xf is equal to xi plus vxt plus 1/2 axt squared. Guys, this is the foundation for a parabolic motion, if you think about this, right? If I take this same equation and I translate this into two directions, x and y, now I have a parabola. I have particle motion. I have a bullet that I can fire in two-dimensional space. I know it's hard to see, but and I'll come back to this in a second. Remember that whenever we have a exponent and I want to solve for t, there's two values of t, potentially, right? A positive value and a negative value. Because if I have a negative and then I multiply it by 2, or to the exponent of 2, it becomes positive, right? So I can have positive and negative values that I'm multiplying by, or putting it to the power of 2, right? So therefore, I have to use the quadratic equation. The quadratic equation, which is x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, right? This quadratic equation, right, is, and we know that we're using this formula for an equation, ax squared plus bx plus c, which we talked a little bit about last week, right? And if I have values that I want to plug in, again, let's look at some values that I want to plug in here, okay? So let's suppose that I'm solving for values of t, right? I'm solving for values of t. And here we're saying for a constant acceleration, this is what we have. If my x initial is 50 and my the velocity of x initial is minus 20, so I'm going in the negative direction. Okay, I'm traveling in the negative direction, minus 20 meters per second, right? And my negative, I have an acceleration that's negative of minus 4.9 t squared, right? And I'm just plugging it into that equation. How do I solve for t? Well, we're going to use the quadratic equation up here, which is, if I'm solving for t, t is really x, right? I'm using this, and I'm subbing in t for x. Instead of ax squared plus bx plus c, it's at squared plus bt plus c, right? All I'm doing is just subbing in the variable. I'm just changing the variable name instead of x and t. Who cares, right? And then what I'm saying is, if I plug in a value of 50 for c, right, and minus 20 for for this, and this is for acceleration, now I'm going to take this underneath the square root sign. It could be a positive, or it could be a negative, right? And so both of these two equations could be correct, right? Why? Because of this. It's plus or minus. It could be plus or minus, which means we might have two y-intercepts, as an example, right? Or two x-intercepts in this case, right? And again, we don't care about negative values of t, but it could be positive values. Why? Because the slope could be to the right of the origin, right? If it's to the right of the origin, I might have two places where that is true, right? However, if one leg of the curve is to the left of the origin, we don't care about that leg because we're time traveling. That's negative time, right? We don't care about negative time, we only care about positive time. But these could be both the same. Why? Because if we take values of b squared, and if we look what b is, ax squared plus bx plus c, this is b, right? Minus 20. minus 20, right? Minus 20 times to the power of 2 is, minus 20 times minus 20, which is 400. That's where 400 comes from, right? 400 minus 4AC, A is this, right? So when we start thinking about the acceleration, 4AC, right? As an example, where A is the thing that's the acceleration, this part, that's 4 times a negative 4.9. AC, C is this, right? All over negative 9.8, right, which is what it was. Okay? There's 2A, 2 times negative 4.9. Okay, that's where you come up with that. So these are just numbers that I'm plugging in, but I want you to see how you would use that equation. And a lot of times, whenever we do this, when we do the quadratic formula, and you can't see the numbers yet, but we're going to come back to them in a second. So we've talked about 4 kinematic equations, and this one, like I said, could be the parabola. It could indicate, like, if I was going to do it in motion in 2 directions, this would be a parabolic motion. Okay, here's, I believe, the last one. Kinematic equation number 5. For constant acceleration, right, we can say that v squared x final is equal to v squared x initial. And this is where we're not given any information about time. If I've never been given time information, and I just want to figure something else out. Let's say, for example, I want to find the final position on the graph if I'm given the initial velocity, the final velocity, and the acceleration. I want to find the final position, but I don't know anything about time. Then I can use this equation. Each equation, if you think about it, has something missing, right? Let's take a look at some of these. So for the first one, it's very simple, right, as an example, and it says does not give any information about displacement. We don't know how much displacement there is. If we don't know the displacement, then we can use this equation, right? This is just to help us with the third equation, but this doesn't give you anything about acceleration. We have no idea about acceleration. We've been given final velocity, initial position, final position, but we don't have acceleration and we want to figure out time. That's why we would use this equation, right? And this one, right, we have a velocity and acceleration, but we don't know what the final velocity is. We have no idea what the final velocity is. We might have an initial velocity, but we don't care. We don't have the final velocity. We know what we're going to end up at, right? We have everything else. So each equation gives us the ability to solve a problem based on stuff that we're missing. Did you have a question? Yeah.
But these were all like doing the same thing, just based on different information.
Yep. Yeah. We're trying to solve a problem, a kinematic problem in one dimension with different kinds of information. We're given different information. We have different equations that can help us. All it is taking the same equation and massaged it in different ways. That's all this is. Okay. So the fifth one doesn't give us anything about time. So those are the 5 equations. What happens? There's a special thing that happens when acceleration is 0. So when acceleration is 0, we can say that VFX final, which is the velocity in the x-axis final, is equal to the velocity in the x-axis initial, which is just the velocity across the x-axis, right? If it's 0, if acceleration is 0, we know velocity is velocity is velocity. That's what we know, right? And the same thing goes with position. If we know that the acceleration is 0, then we know that the final position is equal to the initial position plus velocity times time, right? That's what it is, where time might be 0 a lot of times too. Okay, I can certainly go on, but I want to pause here today. There's 78 slides, and I'm going to post this PowerPoint. Next day when we get together, we're going to do problems for the entire time. I'm going to take some of this and we're going to just do kind of problems about motion in one direction. So we can use these equations for the full class. Right now, I can do it, but it's going to be, probably right now your brain is ready to explode. You need coffee and that kind of thing. I've already bored the crap out of you and bothered some people too, right? And I don't want to bother anybody anymore. I'm saying, that's you, yeah. I don't want to bother you anymore. And I bother the people in front. I've tried to get people to interact, and my friend who was bored left, right? And I don't want to continue without killing you, right? So what we're going to do next week when we get together, this is gonna be the lecture for today. What did we learn? Let's summarize. We learned about motion in one direction. Summary, we learned that distance and displacement are two different things. We learned that velocity, right, and speed are mean two different things. Velocity, if I ask you next week what it is, for you in your mind, velocity is a vector. Speed is not a vector. Speed has nothing to do with direction, right? So those are the things we've learned. We've also talked about manipulating algebra, and what I'm going to do with you guys next week is give you a series of problems. Guys, the problems in the PowerPoints are going to give you practice, and I'm going to give you a bunch of them for the midterm test. The midterm test is going to be, given this, what's the answer? You know, kind of thing. Huh? So you're probably going to have like maybe 60 or 100 questions on the midterm test like this, right? Yeah. Now here's the great thing about the midterm test. You're going to have 2 attempts, right? You're going to have 2 attempts. It's going to be open book, open internet, right? I'm going to give you those kind of things. Is that? I'm never going to make you do it here on paper, right? It's going to be on Blackboard, and you can do it remote for that day, okay? I'm going to be here physically to help you out, but you guys can do remote. So that, you can absolutely calculate it, yes. Everything is online, right? But you need to know the equations, right? You need to know the equations and how to apply them, because, by the way, the answers are going to be very similar, eerily similar. It's going to be like 0.01, 0.02, 0.03, 0.04. Which one is it? And they're very close to each other. You need to know the answer, right? Okay, guys, that's it for me today. Thank you so much. This has been recorded, and I'll put the PowerPoint up shortly. All right, thank you.
Do we need a laptop for the next lecture?
What was that?
Like when you say about solving the problems, do we need to use our laptops? Or?
No, you can do it by hand.